to Math 104. If you flip a total of 100,000 times, then under our assumptions that the first 10 flips are tails, but all the subsequent flips are equally split between heads and tails, and you flip a total of 100,000 times, let's notice first that the subsequent flips, well, how many of them are there? There are 99,990 of them. And they are equally split between heads and tails, which means that there are 49,995 heads among the subsequent flips and 49,995 tails among the subsequent flips. That means that overall, 49,995 out of 100,000 equals the relative frequency of heads. And because we're dividing by a power of 10, we can compute this easily without a calculator. The relative frequency here of heads equals 0.4995. Now that is very close to 0.5. Why is that important? Well, as you keep flipping, assuming that the coin is really fair, the effect of that initial run of 10 tails gradually disappears. Right? In order for this gradual disappearance of the effect of those initial 10 tails to occur, it does not require extra heads to compensate. On the contrary, just having an equal number of heads and tails on all subsequent flips is enough by itself to overwhelm the effect of the initial run of tails. This is enough for the relative frequency to keep getting closer and closer to 0.5. So no extra heads, no compensating heads are needed in order to achieve this. What's the conclusion? The conclusion is that the long-term relative frequency overwhelms but does not compensate. This is why the gambler's fallacy is a fallacy. There's no such thing as the coin had an excess of tails, so now it's due for an excess of heads to compensate. Understanding that the gambler's fallacy is a fallacy, and understanding why it's a fallacy, is part of your education. Everyone should know this, because it is such a common misperception, and people make real mistakes on account of it. The next idea will be very useful for us throughout this course and when you apply what you learn outside the course. An ideal data set for an experiment is a set of experimental results in which the relative frequency of each outcome is exactly equal to its probability. To put that in plain English, in an ideal data set, the long run has already arrived. It's a set of results of performing the experiment that are so perfect that they are, in the short run, perfectly representative of the long-term behavior. I'm not saying this happens in real life, I'm saying it's a useful way to think about experiments. Here's an example. For the experiment of rolling a fair die, an example of an ideal data set is the following. For each outcome, suppose that you have rolled exactly 100 of each number. This implies that in total there were 600 rolls of the die. 100 of each. And because there are 100 out of 600 equals 1/6 of the rolls are ones, the relative frequency is 1/6, and the probability is also 1/6. So the relative frequency matches the probability. Similarly for each of the other values that can appear on the die. The relative frequency equals the probability. I am most emphatically not saying that if you rolled a die 600 times, you would be likely to have this result. No, in fact, if you roll 600 times, it is extremely unlikely that you will get exactly this result. The point of talking about 600 die rolls in which you got exactly 100 of each is that it will make it easier for us to answer certain questions about, and in general to think about, this experiment. For the same experiment, you could write down many different ideal data sets. For example, how about just 6 total rolls of this die? 6 total rolls of this fair die. If you had exactly 1 of each outcome in 6 rolls of the fair die, well, congratulations, you just produced an ideal data set. Because once again, each outcome has a relative frequency 1/6. We can make up lots more. For example, How about 17? Why not? How about 17 of each outcome? That would be a total of 102 rolls of the die. If, in 102 rolls of the die, you produce exactly 17 of each outcome, that too is an ideal data set for this experiment. In fact, any ideal data set for this experiment can be described as a positive integer multiple of this one. That's just another way of saying that in any ideal data set for this experiment, you will have an equal number of each outcome. So we will see that this approach of talking about ideal data sets gives us a very concrete way of thinking about an experiment. This is very convenient because we have rigged the experimental probabilities to equal the theoretical probabilities. To practice this idea, let's look at an example. Consider an unfair die. It's been weighted, it's been loaded in a certain way, so that the following probabilities are associated with each number on the die. We can ask, well, what is an example of an ideal data set for this experiment? We have to think a little bit harder now, but it's actually not so bad. We just need a collection of positive integers to fill in here so that whatever the total turns out to be, the fraction of ones will be exactly 0.14. The fraction of twos will be exactly 0.2. The fraction of threes will be exactly 0.12. Well, the easiest way to do it is just like so. Multiply each one of those decimal numbers that's given by 100. Right? So then the total number of rolls of this unfair die will be 100. If you roll this die 100 times, and 14 of those times out of 100 you obtain a 1, great, then the relative frequency of 1 is indeed 14 out of 100, which is 0.14, and that agrees with the probability, which is 0.14. Great, we made the relative frequency match the probability. Similarly, we've made the relative frequency of 2, which is 20 out of 100. We've made it match the probability. So what did we do? We saw that these were all two-place decimal numbers. We can turn them into integers by just multiplying through by 100. That just shifts the decimal point 2 places to the right. Now take a minute, pause the video, and think of 2 more ideal data sets for this same experiment of rolling this particular unfair die. Think of 2 other ways of coming up with numbers to fill in so that the relative frequencies will match these probabilities. You should really do this. Pause the video. There are, in fact, infinitely many answers, but this one is a particularly convenient one to think about. Here, I've rigged it so that the total is 50 rolls. There are 50 performances of the experiment. Why 50? Because we could notice that the numbers we had earlier, the results of multiplying through by 100 here, these were all even, which means that we can divide them all by 2, and they will still be in the same relative proportions. That means, for example, 1 is occurring 7 times out of 50 in this set of 50 rolls of the die. Well, 7 out of 50 is the same as 14 out of 100. Right? So here, too, 1 is occurring with relative frequency 7 out of 50, which is 0.14. 2 is occurring with relative frequency 10 out of 50, which is 0.20. 3 is occurring with relative frequency 6 out of 50, which is 0.12. So in each case, the relative frequency of an outcome equals its probability, which is already given to us. Now this ideal data set is special among all ideal data sets for this experiment. Why? Because this one cannot be reduced any further. It cannot be simplified any further. The greatest common denominator of these 6 integers equals 1. I couldn't divide through by something to get something even simpler the way I divided these numbers all by 2. The consequence is that every ideal data set will actually be an integer multiple of this one. Just as for the fair die, every ideal data set is an integer multiple of the ideal data set 1, 1, 1, 1, 1, 1, so too, for this experiment, every ideal data set is an integer multiple, a positive integer multiple, of this ideal data set. But there are many more. Another one is, for example, 35, 50, 30, 50, 45, 40. How are you supposed to come up with that? These numbers are just the result of multiplying our fundamental ideal data set by 5. Every entry by 5. 7 times 5 is 35, 10 times 5 is 50, 6 times 5 is 30, etc. That means that our total here is 250 rolls of the die. So in an ideal data set of size 250, there have to be 35 ones, because 35 over 250 equals 0.14. If you're going to have an ideal data set of size 250, there have to be 35 ones. And that is all for now.